So in this class we are going to study electrical circuits. And before I talk about electrical circuits, I usually like to begin by giving the analogy of other kinds of circuits. And in fact, a circuit is anything where some fluid moves around a closed path, the circuit, and it does something useful in that process. The example I give here is a swimming pool with a pump and a filter. And so what happens is the pump here takes the water in and pushes it out through this pipe, and then it goes through a filter, which provides a lot of resistance to the water, but not too much. And then after the filter, the water goes out to the pool where it's collected. There's a large capacity where most of the water is kept in the pool. And then out from the pool is pulled the water, which goes back into the pump, completing the circuit. The two most important things to realize, or to use in this hydraulic example, are the fact that you have something moving, the water, which goes around in the circuit. That's the thing that moves. And there is something pushing, which is the pump in this case. But the pump provides pressure, which is high here on the output, which pushes the water all the way around the circuit, and then the pressure is lowest at the entrance to the pump. So the pump is the source of pressure, and the pressure moves the water around the circuit. Now, in our case, the circuits we're going to be interested in are electrical circuits. And so, while I'll often use the hydraulic example to help with intuition, we really should mostly be thinking of electrical circuits. In this case, the fluid is a fluid of charges, usually electrons, not always, but in most cases it's electrons, because in a metal like copper, some of the electrons are free to wander around as long as they stay in the copper. And like the hydraulic example, we have a pipe, which is the wire, and that's because the electrons are confined to the wire. They can't get out, but they can move along it. However, it's like water moving through a pipe filled with sand, because the electrons move along, but they bump into all the copper atoms or metal atoms that are there, bouncing off them, and that provides a lot of resistance. So we should say what we're going to measure in our circuits. So the things that move, the charges, which we'll usually label with a symbol Q, or big Q or little q, and we measure it in coulombs, abbreviated capital C. Now, to give an idea of how big a coulomb is, note that one electron has a charge, a negative charge, but a charge of magnitude 1.6 times 10 to the minus 19 coulombs. Flipping that over, we see that 1 coulomb would consist of 6 times 10 to the 18th electrons. Now, you may think that that's a lot of electrons, but in any amount of copper, 1 mole of copper, say, which, I don't know, should be several grams worth of copper, there are going to be 6 times 10 to the 24th free electrons. So it contains, several orders of magnitude, say 10 to the 5 free electrons in every mole of copper. And so when the electrons move, they don't move that quickly, but you still get a lot of them moving. That movement of electrons we call a current, and you measure the current by saying, okay, here I have a plane cutting across my copper wire. How many electrons cross that plane at any given time? That's the current. And we measure it, and we will usually use the symbol big I or little I for that. And we measure it in amperes. Amperes is abbreviated with a capital A. And 1 ampere by definition is 1 coulomb of charge crossing a plane in 1 second. Now, the other thing to have in our circuit is what's doing the pushing, and for that we use voltage. Now, the voltage is defined as the potential energy of a charge divided by how much charge is in your particle. So pressure in our hydraulic example was also a potential energy, but that's how much was in a little box of water with the density divided out, and that's how you can get the units of energy. In our case, we take the charge of an electron, say, divide out its charge, and its energy divided by its charge will be its potential energy divided by charge, and so its voltage. Now, as the electron moves from one side to the other, it has a negative charge, so it'll actually gain voltage. But if we instead consider it to be a positive charge moving this way, that charge will lose energy as it bounces off all the stuff in between, and so we'll say that its energy changes by amount delta V, which we measure in volts. So how much its energy changes divided by the charge that's getting changed tells us the voltage. So we define voltage, which we measure in volts, capital V, as 1 volt is 1 joule of energy that some amount of charge has divided by 1 coulomb. So if we took 1 coulomb of charge and moved it in such a way that it changed voltage by 1 volt, it would lose 1 joule of energy. So just to make clear the various links between the two analogies, between hydraulic and electronic circuits. In electronics we have charge, which is like the water moving around in a hydraulic circuit. The pressure moving the water in a hydraulic circuit is like the voltage in electronics. What's flowing, the flow of water, is current in electronics. If we have some big container with a given volume, that goes to the capacitance, which we haven't talked about yet, but we'll have capacitors in electronics. Friction, either because you're flowing through sand or with the walls of pipes, is like the resistance in electronics. However, I really don't know what to make for what the inductance is in the hydraulic example. It's something like the momentum of the water, but it'd be more like a flywheel connected to some kind of mill or propeller in the water, which gets spun up and stores energy. But then if the water drops off, the pump run by the flywheel will push it back, keep it going. Anyway, so there we have circuits. In our case, it's going to be electronic circuits consisting of charges moving around a set of wires and components moved by voltage.